So last time we were talking about the derivative. We just introduced the concept of a derivative, and we started doing some problems. So one thing was to interpret what a derivative meant. And here, if we have S of t is the position function of a rocket, for example, then the derivative would represent the instantaneous rate of change of the position with respect to time. And if we think about it, the change of position with respect to time we interpret as velocity. So here we have a question regarding the velocity and the position of the function. So the question here asks, what is the velocity of the rocket when it is 256 feet above the ground on the way up and on the way down? So here, you have a rocket that goes up, and maybe this is 256 feet is right here. So they want to know what's the speed at this point when the rocket is on its way up, and then the rocket falls and it starts to fall back down. And so they want to know what's the speed at that height on its way back down. So, to me, there's one extremely important word that's being used in this problem. And here it's this word when. So there's two parts here that we want to know. What is the velocity of the rocket when it is 256 feet? So here we want to know the velocity. We want to know something about the velocity at, when indicates that moment of time. And we're given this position. So we have these three ideas: velocity, time, and position. So the first thing is to solve for the when part. So I first need to find when the rocket reaches a height of 256 feet. So you should think about when we say when, we're looking for time. That part I think is important here. So we're going to set the position function equal to 256 because I want to know for what t value, i.e. when, will the position be equal to 256. So, if you look at this equation and interpret it that way, we're set the position equal to 256. So I replace S of t with the position function, which was given. And now we're just doing a math problem. And so here's very important here that, you realize that the way we solve something like this is by factoring. In general, that's how we're solving most things that are polynomial and, involved. So I'm going to bring the two. Actually, what I did here is instead of bringing the 256 over, I wanted this minus 16 squared to be positive. So I'm going to bring this entire term, 160t minus 16t squared, to the other side. And so the 160t becomes negative, the 16t squared becomes positive. And now I want to factor it. And so here, these numbers aren't great for if it was, a test or something, but for homework, these numbers are okay. The first thing to notice is that 16 is a common factor. 160 is 16 times 10, 256 is 16 squared. So we can factor out a 16 and you end up with t squared minus 10t plus 16. And now this we can reverse FOIL. If you think about the factors of 16, 1 and 16, 2 and 8. So that would work right there, 2 and 8. So here I factor it using 2 and 8. And so we get that at 2 seconds and at 8 seconds, the height is 256. Presumably at 2 seconds, that's on its way up. It's at a height of 256. And then at 8 seconds, it's on its way down. It achieves a height of 256. So now I want to find the velocity at these times. So this is the answer to when is the rocket, have a height of 256 feet. So now the velocity function, so from the previous slide last time, we calculated the derivative of this position function was 160 minus 32t. So if you want to review, take a look at slide 5. And we use the extremely long limit definition, which we will review again today. And so once we have the velocity function, we can plug in the times at 2 seconds and 8 seconds. And this problem, in particular, I think brings up the point that velocity is a vector. As you can see here, there's a minus sign here. So this indicates direction. You should think of a derivative as a vector. So here, this is indeed at 8 seconds, it's on its way down. And so the velocity, the negative 96 feet, the negative says it's headed down a speed of 96 feet. And at 2 seconds, again, when we say 96, you should remember there's a plus in front here. And think of this as a vector with magnitude and direction. So this is moving up. So here I finally conclude that the velocity at the altitude of 256 on the way up is 96 feet, the velocity, and on the way down, it's negative 96 feet. And the speed, again, when we talk about a vector, vectors have direction and magnitude. The magnitude of the vector that's velocity is known as speed. And in this case, the speed in either case, whether it's going up or down, would be just 96 feet per second. So we will do a lot more applications with rectilinear motion and the derivative. This is just kind of, to introduce the concept. Anyway, this ends that lecture on section 2.1. So I'm going to switch over now to section 2.2, and we'll talk about the derivative as a function. And so the idea here is that, the derivative is actually its own mathematical object. It does not need any application to justify its existence. Math in general doesn't, it's its own science. And so here we're really looking at the derivative as a mathematical object. The main difference right now that I want you to notice is that in this definition, I say the derivative of a function f of x at any point x is defined to be the function f prime of x. So here, what's changed is that we haven't fixed the point. In section 2.1, we said the derivative of f of x at a fixed point a, where a was a constant. And when we fixed the point, the derivative at a fixed point turned out itself to be a number. So the derivative, we said, is a slope, and the slope is a number. If we allow the input to vary, to be a variable, if we don't fix x to equal a, then when you give me a function, when I find its derivative, the output is also a function. And so this has to do with sort of the mathematical life of a derivative. And that from a math point of view, we see the derivative as a machine that is known as what's called a functional operator. So what that means is it's like a function, except the input is not a number, but a function. So you give me a function, I'll take its derivative, and the output is another function. So here, the input is the function, and the output that the derivative returns is the derivative of the function. So in goes a function, f of x, out comes a function, f prime of x. So that's kind of the mathematical point of view. It's this kind of creature that is able to manipulate functions in some kind of way and create new functions. We'll talk about more what that means. And so I always like to remember this other version of the limit definition of the derivative, and it helps to just look at this and let your eyes get used to it. The commonalities here, if you look in the numerator, in both cases, we have a change in y. The most important thing I can mention is that in both cases, what we're looking at is a slope of a secant line, for example. So in both cases, we have delta y over delta x. In the first case, you have f of x plus h minus f of x, so that's a change in y. In the denominator, think of h as being x plus h minus x. So that's the change in x. So here, think of the denominator as x plus h minus x. Again, with this other, with this other limit definition, the limit as t goes to x, f of t minus f of x over t minus x. In the numerator, I have a difference of y variables. And look, in the denominator, I've got a difference of the inputs, t minus x. And in both cases, the limit is set up to send the denominator to 0. So here, we want h to go to 0. Because remember, in the theory, we're making the point x plus h get closer and closer. We've got a secant line, and we're now making the secant line into a tangent line by moving the second point. A secant line goes through 2 points. By moving the second point closer and closer to that first point that the secant line is going through. So here we want the denominator to go to 0. So in this case, you send h to 0. Here for the denominator t minus x, you can either do the limit as t goes to x, or it's not wrong to do the limit as x goes to t. That will still give you a derivative. If you do the limit as x goes to t, that will give you f prime of t. It will still give you the derivative of f just in the variable t. So, you know, in both cases, I have change in y over change in x, and you're sending the denominator to 0. So important definition that we'll use over and over again, you know, in this section. So now if the derivative of a function does exist, then we say the function is differentiable. Because remember, the derivative is actually a two-sided limit. And the two-sided limit only makes sense if the limit exists. If the limit exists, then we say the function is differentiable. So if the derivative at a point, you know, exists for the function, then the function is differentiable at that point. And if the derivative for the function exists on a whole interval, not just at a single point, but for example, at every point in this interval, not the endpoints. Because remember, the limit is a two-sided definition. At the endpoints, I can't do a two-sided limit. So if the derivative inside exists at every point, then we say it's differentiable, i.e. we are able to differentiate it. And so there's a really important theorem, which I won't prove, but this is something we need to always keep in mind, that if a function is differentiable, then it is also continuous. Now be very careful here. This is a one-way statement. You know, this exact theorem is one of the reasons I wanted to study conditional statements. This is an if-then. If f of x is differentiable, then f of x is continuous. It's not an if and only if. Continuity does not imply differentiability. If a function is continuous, that does not mean it's differentiable. However, if it's differentiable, this theorem tells us then the function has to be continuous. And the proof is in the book. It's not very difficult. I'll let you look at it if you wish. So let me do a quick example. So in all honesty, you know, after Friday, we're not going to be doing derivatives using the limit definition. So here, I'm going to always ask you to follow the instructions. And in this case, they specifically say to use the limit definition. So this is not desirable or fun, but we must know the technique. And again, it falls under the umbrella of just being able to do limits, which is really important, which will come up in a big way in Calc 2. Okay, so here we want to do the limit definition of the derivative. So first I need to know the definition. So this is something I've memorized, you know, this limit definition. And so now remember, in theory, if you try to plug in h equal to 0, you'll get 0 over 0. In theory, the limit definition always gives us something that's an indeterminate form. And so we don't know whether it's going to converge or not until we do the limit and try some kind of math tricks. So here, remember the function f of x is 1 over x squared. So I'm going to replace f of x plus h and f of x with the function definition. So this is f of x plus h. This is f of x. And everything's divided by h. So that's in the denominator here. I just pulled it out. So here's that 1 over h. And then all this stuff here is in the big, is right here. And as I said, if you plug in h equal to 0, the stuff in the brackets here in red will be 1 over x squared minus over x squared, so that's 0, times, here you'll have 1 over 0, so you get 0 over 0. So in this case, looking at the form, so what I really notice is an algebra thing, that these are two fractions that can be combined. So that's what I'm going to do. I multiply the first fraction top and bottom by x squared. The second fraction, I multiply top and bottom by x plus h squared. And now we need to just keep doing the algebra. Again, here, if you apply the limit as h goes to 0, you get 0 over 0. So now I need to FOIL this out and you know, see if stuff will cancel. So FOILing out x plus h squared gives me x squared plus 2x h plus h squared. And now, you know, I think it's really important to remember that this minus sign here is going to distribute across every term. That's why I'm very careful about writing my parentheses. So this minus sign, we're going to distribute. So I get x squared. When I distribute that minus sign, I get x squared minus x squared. So this term and this term cancel. And then I have a minus 2xh and a minus h squared, which is exactly what we have here. Minus 2xh minus h squared with the x squareds canceling. Again, if you try the limit, you get 0 over 0. You know, here the thing is just to follow the algebra all the way through. What you should notice is we have a common term. H is a common term. Let's factor out the h. And that's good because we've got an h in the denominator waiting where we can cancel it. So here I factor out the h in the numerator. Then I cancel this and cancel with the denominator. So the limit looks like this. So now try the limit. Plug in h equal to 0. I'm plugging in two different places. I'm plugging h equal to 0 right here and right here. Remember this term x plus h quantity squared, when I plug in h equal to 0, this term here just becomes x squared because the h disappeared. And I have x squared times x squared in the denominator, so you get negative 2x over x to the fourth, and then I cancel an x. So yeah, it's a lot of work for, you know, not that thrilling an answer. There's the derivative. And as I said, we will learn shortcut rules and we will stop doing derivatives this way very soon, starting on Friday. But it's really important that we're always aware of what we are shortcutting. You know, it's important that we don't reduce math to just memorizing a series of steps. That might work in Calc 1 or Calc 2, but then it stops working as you start to go higher and higher level math. Remember, Calc 1 will be the easiest math class you take in college, right? So here, if fx is 1 over x squared, we showed the derivative is minus 2 over x cubed. What you should notice is, given a function, I plug it in and to the derivative machine, and the derivative machine spits out a function, right? So function in, function out. Function in, function out. So that's kind of the math point of view of a derivative as what we call a differential operator that's relating certain spaces. You know, I won't get into it too much. So now we want to talk about what are called tangent lines and ways a function cannot be differentiable. So one of those ways is when we have a vertical tangent line. So that's how that's connected. But first, let me talk about what's called a horizontal tangent line. So a function basically has a horizontal tangent line if the slope of the tangent line at that point is 0. So the slope at the point x equal to a of the function is 0. So let me do a quick example here. So if we have a function that's kind of a parabolic shape like this, any point on the graph where the slope is 0. So here at the very peak here, for this graph, right there at the very peak, the slope of the curve, the slope of the tangent line is 0. And think about what that means. When the slope is 0, the slope is rise over run. So if the slope is 0, that means the rise is 0. There's no movement in the y direction. You've got 0 in the numerator. So here, when the slope is 0, the function is, you know, purely moving in the horizontal direction. There's no vertical motion. And at that point, we have a horizontal tangent line. This will be useful later for finding the high points and low points of functions, because we're really interested in analyzing the behavior and shapes of curves. This comes in handy when we're designing roads, roller coasters, any object that involves shapes, you know. Especially when we're trying to manufacture something, we'd like shapes that have equations to them so that we can reproduce that shape not just hand drawn. If we hand draw things, then we need molds. The opposite of a horizontal tangent line is a vertical tangent line. So vertical tangent line occurs at a point that's number one in the domain of the function. So first of all, here I make this comment that f of x is continuous at x equal to a. So in particular, that says this number a is in the domain of the function. So the function's defined at a, but the derivative at a is not defined. So let's look at this very closely here in the red box. So here we're doing a limit as x approaches a from the left of the absolute value of f prime of x, and we want, if that equals plus infinity, then we have a vertical tangent. So the absolute value part, this is just a handy way of saying if the limit as x approaches a from the left is either plus infinity or minus infinity. So if you take the absolute value, then it'll equal plus infinity. So here, it was just kind of, you know, a shorthand notation instead of writing if the limit of x, the limit of f prime of x as x approaches a from the left is equal to plus infinity or minus infinity, you can also write it this way. Or if the limit as x approaches a from the right, again, is plus infinity or minus infinity, then we have what's called a vertical tangent. So in particular, take a look at this picture, and I want to show you, if you look at the, remember we always look at the picture from left to right. So here you see the slope is negative, but as we're getting closer and closer, the slope is getting more and more negative. It's getting more and more negative. So at this point, when it gets to here, we assume that it's got that the slope is completely negative, i.e. it's negative infinity. So you should notice these red slopes are getting, it's starting out negative and becoming more and more negative. And so by the time we get to this vertical position from the left, we interpret that as being negative infinity. That slope right there, vertical slope. And for this other box, so here, let me show you how this is working. So here, this is approaching a from the right. So in this picture, what we see is the slope is going to plus infinity. So if you look at this slope right here, again, let me use a different color. It's a little better. Here, look at this slope right here. Look at the slope from left to right. Okay, that's a positive slope if you look at it left to right. As we approach a from the right, keep looking at the slopes left to right. You see it's still positive, but getting steeper. As we approach, this vertical line gets steeper and steeper. And so we interpret the slope here as getting steeper and steeper going to plus infinity. So this exactly would be this limit here. This would be approaching a from the right, and the slope here would be blowing up to plus infinity. If you want to see a picture of x approaching a from the right and the slope's going to negative infinity, then just flip this image upside down. This same image, if you flip upside down, you get the opposite. Here I have a positive slope that's becoming more positive as it goes into this vertical piece. And you know, before the tangent here, if you flip it upside down, did I flip it upside down before? Sorry, here's my positive piece. Sorry, I don't think I flipped it upside down before. Here's the positive slope. Getting more positive finally goes to plus infinity. Or from the other side, look at it left to right. That's a negative slope. Getting more negative, there's your negative infinity. Another way vertical tangents can happen, I'll show you here in 1 second, is if you take half of this picture and flip it. So just take one of these sections and flip it upside down. And I'll show you a picture of that in a second. Flip this upside down so that it kind of looks like an S. So right there, we'll have a vertical tangent. And I'll show you a picture of that in 1 second here. So in general, a function will not have a derivative, obviously at a vertical tangent. At a vertical tangent, you can see the derivative is literally undefined. The derivative is either plus or minus infinity. And plus and minus infinity aren't numbers. The only way a limit can exist is if the limit equals a finite number. So here, the limit of the derivative literally does not exist, so it's not differentiable at a vertical tangent, but it could also not be differentiable at a discontinuity. That's because of the previous result. We said differentiability implies continuity. So if it's not continuous, it can't be differentiable. And finally, at a cusp or a corner. So a cusp or a corner is basically when the limit from the left is a finite number for the derivative, and the derivative from the right is a finite number, but they're different numbers. So here's a picture. This first one right here is a cusp. And you see, you know, the main difference between a cusp and a vertical tangent is the slope right here is a finite number. It's not going to infinity. So this, it stops right there, and maybe the slope there is like 2, and the slope on the other side is also a finite number, but it doesn't go up to infinity. So here in both cases, the slope from the left, the slope from the right are finite, but they're not the same. One's positive in this case, one's negative. Really famous example is our absolute value function, which has a full-on corner in it, right? You remember the graph of the absolute value function, you've got y equal to negative x, and then once you get to 0, it's y equal to x. And it has, you know, just a flat out corner in it where the function will not be differentiable. The derivative from the left here is negative, the derivative from the right is positive. I'll do the absolute value as a separate example here in 1 second. So yeah, that's a cusp or a corner. Again, differentiability implies continuity. So if the function is discontinuous in any way, here we have a jump discontinuity, but if it has a removable discontinuity or an infinite discontinuity, you know, you're not going to have differentiability. Of course, if it's an infinite discontinuity, then that's like a vertical asymptote. So obviously the derivative doesn't exist there. And then finally here, this vertical tangent, which we talked about. So these are 2 different examples of vertical tangents. And like I said, if you flip this picture upside down, that's also an example. And if you flip this picture left, right, so you'd have vertical tangents. These are the 4 ways you can have vertical tangents. Kind of at a kink, or at a, like a S-like shape here where it's going vertical. This is like the cube root function. And it's different from the cusp or the corner, okay? So let's, so this is important. These are basic kind of features, you know, we're always worried about where a function is not differentiable or where a function has a vertical tangent or a horizontal tangent. So these are basic concepts in analyzing the shape and behavior of a graph. Here's one thing to think about. Suppose you're in a spaceship. So here's my spaceship. I went with the triangle design. Suppose you're in a spaceship and you wanted to land your spaceship. The one place I would not want to land my spaceship based on this pictures is where it's not differentiable. Where the ground is not differentiable seems like a terrible place to try and land a spaceship. Okay, so the differentiability is really important on many, many levels, and we'll talk about it. Not just this spaceship analogy, which is a very valid, you know, situation. It's definitely, if we're landing our spaceship, we want to try and find a nice differentiable spot to put our spaceship down on. So let's do an example here. Let me talk about the derivative of the absolute value function. This is not a hard problem, but this is a very important problem. There's a lot of good theory and concept here, okay, and a good review of limits. So for the absolute value function, there's 2 questions here. Find the derivative at a single point, and then find the derivative function. So, you know, you should think about the difference here. F prime of 0, this is going to be a constant. F1, F prime of x, this is going to be a function. So I'm going to do F prime of 0 first, and I'm going to use the standard definition. So here, F prime of A equals, the limit is h goes to 0 of f of a plus h minus f of a over h, but a here is 0. Now I'm going to simplify this. So look, f of 0, f is the absolute value function. The absolute value of 0 is just 0. So this is going to disappear. 0 plus h is just h. So really, I'm just doing f of h over h. F of h is the absolute value. Okay, so I'm doing this limit of absolute value of h over h. This is 0 over 0. And in this case, based on the definition of the absolute value function, we're going to want to look at the one-sided limits based on the, because from the left and the right, the absolute value behaves differently. So taking the limit from the right, as you know, when h approaches 0 from the right, h is greater than 0. If h is greater than 0, the absolute value of h just equals h. Cancel, cancel, the limit from the right is 1. The limit from the left, h approaching 0 from the left means h is less than 0. When h is less than 0, the absolute value of h is just negative h. Again, cancel, cancel, limits minus 1. The limit from the left and the right do not agree. Therefore, the derivative at 0 does not exist. Let's calculate the derivative of the function in general. So here I conclude the function, the absolute value function, is not differentiable at x equal to 0. In this case, because there's a corner. The derivative from the left is -1. The derivative from the right is +1. There's a corner. Now to calculate the derivative in general, rather than do the limit definition, I'm going to use the idea that the derivative is the slope. So before we use the derivative to find the slope, here I'm going to find the derivative by figuring out the slope. So here, if the function's f of x, I know its slope is m equal to 1, and the slope is the derivative, so the derivative of x must be 1. Similarly, the slope of f of x equal to -x is -1, and I know the slope and the derivative are the same, so the derivative of -x must be -1. And so now I can write down the derivative of the function absolute value of x is going to be 1 if x is greater than 0, because that's the slope of x. And it's going to be -1 if x is less than 0, because that's the slope of -x. Now be very careful. At x, it's not defined. You see here, I did not put an equal in. Sorry, not at x. At 0, it's not defined. I didn't put an equal symbol in here for the derivative because we just showed the derivative at 0 does not exist. So that part's really important. If I wrote this equal symbol here, that would be incorrect. So it's really important you notice there's no equal symbol right there in that domain. And that has everything to do with, you know, the function not being differentiable there. So this is a really good prototypical example. It's not difficult, but there's a lot of good theory here. And it helps the brain to go over this a couple of times. Because, you know, this is a little weird, I think, for the brain. And then to use the two-sided limit is something we have to, the one-sided limits, excuse me, is something we just have to keep remembering in which scenarios we need to use it. Here, because the numerator changes its definition on either side of 0, we need to check the one-sided limits. So here, I wanted to find a vertical tangent line. So this is a vertical tangent line problem. So now be very careful. A vertical tangent is different from a vertical asymptote. Okay? So a vertical tangent, actually, you can think about it this way. A vertical tangent is a vertical asymptote of the derivative. So when they say find all vertical tangent lines of the positive square root function, they're just saying find all the points where the derivative blows up to infinity or minus infinity, where the derivative, you know, look for the zeros of the denominator of the derivative, if there are any. So here I'm first going to find the derivative. And I'm going to use, in this case, I use the other definition. You can use the f of x plus h minus f of x over h as h goes to 0 definition. You'll get exactly the same answer. So here I plug in the functions. It's 0 over 0. Based on the form, I multiply by the conjugate. So based on what I'm seeing in the numerator here, and since it's 0 over 0, I'm multiplying top and bottom by the conjugate. The numerator simplifies to t minus x, which is good because I can cancel t minus x in the numerator and denominator, and then apply the limit. Here, plug in x for t. So in the denominator, I have root x plus root x, so I have 1 over root t plus, you know, root x, and then you add the 2. My final answer here for the derivative is 1 over 2 root x. Now look, I'm looking for points where the derivative is undefined, but the function is continuous. That's part of the definition of the vertical tangent. It's a point where the original function is defined and continuous, but the derivative blows up to infinity. So here I just make this comment that our original function is continuous at x equal to 0. That 0 is in the domain of the original function, no problem. X equal to 0 is in the domain of square root of x. But it's not in the domain of the derivative. So here, however, it's not in the domain of the derivative. Once I verify that the derivative is blowing up to infinity, which I do with the limit here. So I take the limit as x goes to 0 from the right. So the first thing you do with the limit is plug in. So when I plug in, I get 1 over 0. And in a one-sided limit, number over 0 is either plus or minus infinity. In this case, this is always positive, right? That's the positive square root in the denominator. So here it's plus infinity. So here we have a vertical tangent line at x, at the origin. So now think about the graph. It's important now. Think about the graph of the square root of x. You remember the graph looks like this. It starts out at the origin, goes straight up, and then curves. Right here at the origin, we have a vertical tangent line. You can see if you take the limit coming in from the right, so take a limit like this, the slope is positive, getting more positive, getting steeper and steeper. Always look at the slope left to right. So by the time we get to the origin, it's at plus infinity, and there's a vertical asymptote there. Alrighty, folks. So, we said the derivative is this machine. You give me a function, I put it in the derivative, it spits out a function. Well, why can't I take the function that the derivative spit out and put that back into the derivative machine? Well, we can. And I'm sure, everyone's happy about it. So we can talk about the derivative of the derivative, or the derivative of the derivative of the derivative, so on and so forth. So we define the second derivative of the function f of x, which we write as f double prime, the double prime to indicate a second derivative. We define this to be the derivative of the derivative. So here's the limit definition. I'm just doing the limit definition. The only difference is instead of having an f here in this limit definition of the derivative, I'm now applying the derivative definition to f prime. And if this limit exists, that'll give me f double prime, or the second derivative, which we ostensibly interpret as the instantaneous rate of change of the slope of f, the rate of change of the rate of change. Eventually, we'll see that can be interpreted, depending on the situation, as acceleration or a thing that's called concavity. We'll talk about those concepts later. And so I say here higher derivatives, not just second derivatives. We can keep playing this game. I can do the limit definition of the second derivative. So I'm adding here the second derivative, that if that limit exists, that gives me what's called a third derivative. And I can take the derivative of the third derivative to find the fourth derivative, so on and so forth. So let's introduce some notation for this. So we did define the 0th derivative. So on the left, on the right here, this is the 0th derivative of f is just defined to be f. And we use this parentheses notation. This is not an exponent that indicates a derivative. By definition, the 0th derivative is just f. The first derivative, f prime, we would write as f and then a little parentheses 1. Again, remember, this is not an exponent. When we put a parentheses around it, this indicates the order of derivative. So the second derivative would be f parentheses 2, third derivative would be f parentheses 3, and so on and so forth. And so now we can define in general the nth derivative, where n can be any integer. So here we could be talking about the 50th derivative, the 100th derivative. And so we define it basically recursively. The nth derivative is just the derivative of the previous derivative, right? The nth derivative is the derivative of the n minus first derivative. So in this equation here, if we make n equal to 2, so here if I let n equal to 2, then we get, if we say let n equal to 2, then this gives us exactly this equation. F double prime is the same as f parentheses 2. And so here, let n equal to 2. Here you get f parentheses 1, which is the same as the first derivative. So we'll use this notation a lot. So if it looks a little weird to you, it's okay. You know, don't worry, we'll use it a lot. And this notation comes up a lot in Calc 2, the parentheses notation for derivatives. Okay, we'll practice with it and it'll get better. With notation, the more you can practice with it, the better it gets. It's not anything natural. It's just about practice, and practice makes perfect. So we also have an alternate notation called Leibniz notation. So calculus is typically attributed to Isaac Newton and Gottfried Leibniz. Here, the Leibniz notation treats the derivative more as this mathematical thing we call an operator, a differential operator. So what does that mean? An operator is the idea that it's like a function, but it's a function of functions. That's why we use the word operator instead of function. So the input is a function and the output is a function. So here, the differential operator, Leibniz uses d divided by dx. It looks like a fraction, but it's not a fraction, okay? So here's how the notation convention works. So if I want to express f prime of x in Leibniz notation, well, what I'm doing is I'm taking the derivative, interpret d dx as the derivative with respect to x of f. And now this letter f, I can just put it up here in the numerator. And you can write this as df dx. So when you read df dx, you should read this as the derivative of f with respect to x. That's exactly what this is saying. The derivative of f with respect to x. It's the same exact thing. And now the second derivative. As you remember, the second derivative is the derivative of the first derivative. So here I'm doing the derivative of the first derivative, d dx of df dx. And now we kind of do this fake math here. The d times d, we say that equals d squared, even though this is not an exponent. This square from context actually represents a second derivative. That square there really represents a double prime or parentheses 2. It's all from context. And in general, for the nth derivative of f, I would be taking the derivative of the previous derivative. And so the nth derivative would look like dnf dxn. So for example, a third derivative would look like d3 here. I don't say cubed because it's not really an exponent. F over, other people do say cube, dx. And then here, you know, I'll say cube, but it's not a cube. This is to indicate the derivative. Again, if you're not too comfortable with this notation, that's okay. We're going to use this notation over and over and over and over again, and you'll be surprised what your brain will get used to. And you know, it'll just be like drinking water. It'll be just easy when you look at it. Just takes time though. Practice makes perfect. One final comment about the notation, and this is a really important comment. When we see this notation f prime of a, we interpret that as first find the derivative, df dx, where x is just a generic variable, then plug in x equal to a. If you do it the other way, if you first plug in a into the function and take a derivative, typically a is a given constant. So if I take a and plug it into the function first, that becomes a constant because I plugged in a number for the variable. And then if you take the derivative of a constant is 0 because there's no rate of change. So if you plug in the a first and take a derivative, you're always going to get 0 as your answer, which is incorrect. So when we write f prime of a, we specifically mean first find the derivative and then plug in x equal to a. And we use this long vertical bar with x equal to a at the bottom to indicate we're going to replace x with a after we find the derivative. So here, I would interpret this notation here as first find the derivative of f with respect to x, then plug in the number a for the variable x. So that's the same here. I rewrote it here. We have, here's the derivative of f as a function, as an input-output, and now we're replacing the input with this constant a. And in both cases, that's the same as f prime of a. Find the derivative first, then plug in the number. All right, let me do this last slide here, and I'm going to stop. So this slide is just an example of higher derivatives. We talked about if s is a position function, then the derivative of s would be the rate of change of position with respect to time, which we interpret as instantaneous velocity or just velocity of the object. And so here in Leibniz notation, so we said in Newton's notation, we said v of t equals s prime of t, or in Leibniz notation, s prime of t looks like ds dt. The derivative of the position function, first derivative of the position function with respect to time. And the derivative of the velocity, rate of change of velocity with respect to time, is known as the acceleration. So the acceleration is the derivative of the velocity. So in Leibniz notation, I can write it as dv dt. But remember, v is itself a derivative. So here, v itself is this derivative here, ds dt. So I'm going to replace that v with ds dt. And so now look, if you do this kind of fake math here, I have a d times d, which will give me this d squared in the numerator. And then in the denominator, I have two dt terms, which gives me this dt squared. Remember, these aren't powers, they're actually orders of derivative. So here we see, oh, the velocity is also the second derivative of the position function, which we can also write this way. Here, there's not a lot of math happening here. Here, you're getting comfortable with the notation. And it's okay if right now it's a little bit weird and confusing, that's fine. We're going to keep working with it till you get comfortable with it. One more, you can take the derivative of the acceleration. The rate of change of the acceleration with respect to time is known as the jerk force or jolt. You know, you can compare someone who accelerates very fast or someone who accelerates very slow. The jolt is different. So here, the jolt is defined to be, as I said, it's the derivative of the acceleration, which means it's the derivative of the second derivative of position. So it must be the third derivative, right? So here, d dt of d squared s d dt squared would be d cubed here, because I took the derivative of the second derivative. So I'll let you think about the notation, and it's also, you know, the derivative of, it's the second derivative of the velocity, right? Because it's the derivative of v prime. So I'll let you think about the different derivative relationships between these things. Remember, none of this stuff will be on the exam this Wednesday. This will all be on the exam in March. You know, by that time, we will have worked with it so much, it'll be a lot better. I'm going to stop right here.